Hello everyone and welcome to the 47th session of the Porous Media Tea Time Talk. Today's seminar is dedicated to Heriot-Watt University, which will host the InterPore annual conference in Edinburgh next week. So we will have the pleasure to hear from two junior researchers from this university. I'm Sarah and I'm joined here in the studio by Chiara, Federico, Marcel, and Madi, who are organizing members of the PNTTT and part of InterPore Young Academy. Our first speakers today is Hariharan Ramachandran, who is currently working as a postdoctoral in the MUFI research group at Heriot-Watt University. His research centers around developing methods for fault representations in vertical equilibrium modeling. Previously, he was employed as a postdoc at UiT Arctic University of Norway, where he focused on examining methane seepage and related gas hydrate system in the West Svalbard market. He received a PhD and master's degree in petroleum and geosystem engineering from the University of Texas at Austin, and a bachelor technical in chemical engineering from Anna University in Chennai in India. So today his talk will be about a quick approach to model fault leakage during CO2 storage within vertical equilibrium modeling. And then Hariharan, thank you for being here first, and the floor is yours. Sorry, you're muted.
Thanks, Sarah. Thanks for the introduction. My name is Hariharan. Hello, everyone. Good afternoon. My name is Hariharan. I'm a postdoc in the MUFI research group at the Heriot-Watt University, and I'm excited to share some preliminary results with you all in this talk. So I will discuss the modeling of fault leakage within a vertical equilibrium approach and highlight its importance as a fast and effective tool for screening CO2 storage reservoirs. Before we begin, I'd like to thank my supervisors, Florian Doster and Sebastian Geiger, for their support. So I'd like to begin this talk by setting up a motivation for CCS. CCS, or carbon capture and storage, involves capturing CO2 from stationary sources and safely storing them in the subsurface formations, such as depleted oil and gas reservoirs, saline aquifers, etc. And the goal here is to mitigate or at least slow down climate change. Diving in, like any large-scale projects, CO2 storage has its own inherent risks. Understanding these risks involving assessing the event likelihood and the resulting damage. So here we specifically focus on the risk of leakage along a fault. As you can, I hope you can see the mouse, so you can see the fault blow up here. So I'd like to blow a typical CO2 injected at the subsurface can potentially leak if it encounters a pre-existing or a reactivated fault pathway. Blow up of a fault pathway is shown here. So there are two possible scenarios for leakage. CO2 can either leak if it flows through the damage zone, which is assumed as an equivalent porous medium, or it can flow through the fracture network, assuming that the damage matrix has extremely low permeability. So the flow properties of the fault zone will strongly depend on the complex interaction between this fault zone matrix, the fracture characteristics, such as the aperture, width, length, etc., and the effective stress in the system. And developing these relationships require extremely specialized experimental characterization. Now, taking an overall project perspective, these faults pose a particular risk as smaller faults can be easily overlooked during the field exploration or characterization phase, or they can exist far away from the monitoring or injection well, making the detection challenging. So this becomes especially critical during the concept selection phase when the data is limited and the uncertainty is high. So conducting a full-scale 3D flow-coupled geomechanics simulation to resolve this issue will be a computationally expensive method. So our goal here is to assuage this problem by developing a fast screening method using a multi-scale, multi-physics approach within a vertical equilibrium modeling setting. So there are two key advantages for doing this. One, this is really quick. It gets the fault leakage estimates for a wide range of uncertainties quickly. And two, we can quickly identify n-member scenarios which need further investigation using, say, a full-scale 3D flow and geomechanics simulation. So in the following slides, I'll present two key results. One for a leakage, assuming it happens through the damage zone, and the another with leakage occurring through a fracture network setting. But first, let's look at what a vertical equilibrium modeling approach is. Now, a typical CO2 storage reservoir, there are two key requirements to use a vertical equilibrium approach here. One, the reservoir needs to be a thin and long because this results in a minimal vertical flow when it compares to the overall flow in the system. And two, it is located deep enough that there is significant density differences between the brine and CO2, leading to a faster fluid segregation. Like once the CO2 is injected, it typically goes to the top of the reservoir and the fluids tend to segregate quickly, like into separate CO2 and brine zone. And there will be no vertical flow between these zones. So once this thing is established, this results in a vertical pressure field being in a fluid static equilibrium or vertical equilibrium. So we can take advantage of this feature in our simulations. So for example, in a conventional 3D simulation grid as shown over here, what we assume is at every grid block, there is a local equilibrium, which means that the pressure, temperature, saturation remain constant within each block. Now, if we assume a vertical equilibrium situation, the pressure and saturation is assumed to be in an equilibrium within a vertical column over here and can be represented in terms of an upscaled variable as a function of gravity, capillary pressure, among several others. Now, this simplifies this model from a 3D setup over here and compresses into a 2D grid as shown over here. Now, this reduces the computational costs substantially, and the vertical pressure and the fluid distributions can be reconstructed from the upscaled variables into a 3D grid in the post-processing stage. Now, I can show you an example for this simulation where we present a simple 2D case of a CO2 injection in a well located in the middle of the reservoir, which is the well is over here. Now, all the simulations were performed using an open source MATLAB reservoir simulation toolbox, and the resulting gas saturation evolution is shown over here. The top simulation shows the fine scale simulation for the gas saturation evolution, while the middle simulation shows the VE grid, which is obtained by compression. Now, the 2D grid had close to 5,000 grid blocks, but on compression, we had only 100 grid blocks in this 1D grid. Once this gas saturation is solved in the VE grid, we can reconstruct it by using these upscaled variables, and then we get this final result in this 2D grid post reconstruction. The key takeaway here is that despite the reduction in dimensions, the upscale variables implicitly captured all the physical behavior observed in the full system. So this gives us a lot of computational advantage. But then there is one point of note that we have to take into consideration, that in a typical fault leakage scenarios, most of the leakage is going to be vertical. So this challenges the assumption of vertical flow in a VE framework, and especially if this vertical flow is significantly larger than the horizontal flow. So this throws an important question on how are we going to model this VE fault leakage within a VE framework. So in the following slides, we propose a hybrid modeling approach to solve this issue. So what we do is we combine this VE grid with a bit of fine grid simulations, and then we use another approach where we combine this VE grids with a non-neighboring connector approach inspired by the embedded discrete fracturing modeling setup. So before doing all this, I would like to set up a base case scenario, which we are going to use for the comparison for all the approaches I discussed. So an illustration of a three-layer grid, three-layer reservoir is shown over here, and the corresponding grid I've shown on the right, and the corresponding permeability in this region is shown below. So what we have is a three-layer system where the target reservoir with 100 millidarcy permeability is shown at the bottom. A middle cap rock layer with close to 1 microdarcy permeability is shown in the middle, and the secondary reservoir with 100 millidarcy permeability is shown at the top. The CO2 is injected into the bottom reservoir, and then once it leaks, it comes out of the top reservoir. That's the idea we're going with. And then we have introduced a 5-meter fault block with 1 millidarcy permeability that connects these two reservoirs at the cap rock layer, which at the cap rock, at the end of the cap rock, and this represents the flow through the damage zone scenario. Now the system is divided into 12,000 grid blocks, which each grid block being 1 meter long and 25 centimeters tall. So we have assumed a simple core type rel perm for the fluid phases, and the capillary pressure is neglected in the system. So the dark planes you see in this grid are the no flow boundaries. So we assume that there is no flow through these boundaries. So for example, the top and the bottom have no flow boundaries, and similarly the right extreme is assumed to be a no flow boundary. This is to represent a fault core with a very, very low permeability, and a constant pressure boundary is given by the hydrostatic gradient is maintained on the left extreme, which is shown by the red line on this grid this thing. So this pressure is given by the hydrostatic gradient, and this hydrostatic gradient pressure is maintained at the top reservoir and the cap rock. And for the bottom reservoir, we have slightly modified this pressure boundary condition. And the pressure is to represent a vertical column, which has 3 meters of CO2 in the top and 7 meters of water in the bottom. So the pressures and saturations are modified accordingly in this boundary so that the CO2 influx happens. And most of the CO2 influx is going to be a buoyancy driven system. And for the comparison, we are going to take 3 key variables into account. I can show you the simulation over here for this fine scale. We are going to take into account these 3 key values. The one is the time taken for the CO2 to exit from the top grid block as shown by the circle over here, and from the top reservoir. And 2, the amount of gas flux entering the reservoir at the bottom, and the amount of gas flux leaving the top of the reservoir. So now this is the key variables we are going to use it to compare with the other approaches. Yeah, so now the first hybrid modeling approach we'll discuss is the VE plus fine scale grid approach. The illustration of the fine scale grid and the base case is shown at the top. So now what we are going to take in this approach, we are basically going to take into advantage both the advantage of VE grid and the fine scale grid. So at the regions where the horizontal flow is going to dominate the vertical flow, we can represent them as VE grids, like the middle section of the reservoir. And at regions where we expect substantial vertical flow, we can retain the fine scale grid, such as at the boundary blocks and at the fault grid blocks. So I've shown the VE grid in the image over here, where you can see there are fine scale grids at the top reservoir, left boundary, and the right boundaries, and at the fault blocks. These are the blocks with the fine scale grid. So now this original 12,000 grid block problem has been reduced to around 1250 grid blocks as shown here. So now everything else is kept as constant at the same place. And the one major point of note over here is we're still treating the fault as an equivalent porous medium or flow through the damage zone. And we continue with this assumption. So I'm showing you the gas saturation evolution for this 2 approaches here. So the plot on the right you see here is the gas flux out of the top of the reservoir normalized by the amount of gas entering the bottom reservoir is shown here. So what we can clearly see is that the results from the hybrid approach matches really well with the fine scale simulation. And the major implication is that this approach could be used as a replacement even for the fine scale simulation, because in spite of reducing close to an order of magnitude of the grid blocks, we're still able to capture the fine scale simulation. Now, there are 2 directions in which we can take this research forward. One, we can add different values to the rock and rock fluid properties for the reservoirs and faults. For example, we can include different capillary pressure curves for the reservoir, for the faults, and study the impact of capillary entry pressure on fault leakage. We can couple it with the geomechanicals model, for example, and then predict the impact of effective stress on this fault zone permeability. That is one way to take this forward. And the other approach is we can identify what is the minimum number of fine scale grid blocks necessary for this hybrid approach to accurately represent in a fine scale simulation. For example, whatever result I've shown here has close to 1,000 fine scale grid blocks. The question is, do we really need 1,000 grid blocks, or can we do away with even 500 or 600? So all these optimizations are helpful, and it will lead in computational benefits, especially when you're doing a large scale uncertainty quantification study with a relatively low amount of data. And in the second hybrid approach, we will discuss the combination of a VE and a non-neighboring connector approach, or the NNC approach. The illustration and the fine scale grid of the base case scenario is shown at the top. Now, NNC is short for a non-neighboring connector. And just like the name suggests, it connects 2 grids which are physically apart from each other. So they're commonly used in a commonly used to connect discrete fractures and the surrounding porous medium in an embedded discrete fracture modeling framework. We are borrowing this concept to connect like 2 VE grids over here. So now both the reservoirs from the previous grid are represented as a VE grid as shown over here. And instead of the fault blocks, these 2 VE reservoirs are connected using a 2D vertical plane, which is treated as a non-neighboring connector or NNC, as shown by the red plane over here and a red line in this illustration. So the grids are then coupled to each other via source sink relations, and we use a transfer function to transfer the fluxes between the VE grid and the non-neighboring connector grid. So the key point to note over here is now that we are treating this fault leakage as a fracture network scenario and not previously where the flow is happening through a damage zone. So I can show you the gas saturation evolution for this result. First of all, I have to make a small apology where you do see some gas saturation variation in this VE plus NNC plot, but this grid is still in the vertical equilibrium grid, and I have not reconstructed the gas saturation into a regular grid. But you do see changes in the gas saturation as evidenced by this gas flux plot over here. So what you see is this gas flux, the normalized gas flux. There is a reasonable match with the fine scale grid, although the breakthrough times at which it comes out is faster than the what you see in the fine scale grid. So the minor difference is mainly because of uh, the way we treat the transfer functions between the VE grid and the 2D fault plane. So now this is a key result where we have a reasonable match. Now there are two directions in which this research can be taken forward. One of the reasons why this is match is because the transfer functions didn't work. So this is the reason for future investigation where the flux through the NNC is strongly coupled between the transfer function between the VE grid and NNC grid. Currently, for this work, I've used a very simplified approach where I've only taken the reservoir permeability into account. If we add more physically representative transfer function, for example, we can include the capillary pressure or relative permeability into this transfer function, that will greatly enhance these comparisons. So we can also scale the capillary entry pressure, we can scale the relative permeability endpoints into this. So that's one way to take this forward. And the other approach it opens up an avenue to represent this entire fault zone as a fracture network instead of a damage zone. Although we are showing only one network between these two VE grids, this leads to a scenario where we can investigate multiple networks between these VE grids in the future. For example, we can, as you can see the image here, where we can put a lot of fracture networks between these two VE grids, and we can investigate what the fault leakage is going to be. And also we can study how this fracture network interacts with this fault zone matrix during leakage. Further on this, we can also include the effect of effective stress and its effect on fracture aperture and there are several ways to take this forward. So this is where we are in this research, and we are just filled with a lot of opportunities to take this forward and interesting this thing. So a brief summary of what I've said so far, that the faults blocks as a proxy is a fast method for assessing leakage risk. The VE plus fine hybrid, although gives you an order of magnitude reductions in the grid blocks, is a very good replacement for fine scale simulations. And this VE plus NNC hybrid also opens up a lot of opportunities to the way we imagine fault modeling and the effect of fractures at network in it. And in the future, we'll add all the fault and caprock seal characteristics into this, like I mentioned. And we'd like to acknowledge the general support of Petronas for this research. Thank you.
Thank you very much, Harry. Very beautiful talk. So we'll go through the questions if you have any. Let's see. Okay, we have a question saying, great talk, Harry. Sorry I joined the talk a little later, that might have missed. I was wondering about validation for various parameters. How do you approach this?
What parameters are we talking about now? Validation for which parameters? Are we talking about the reservoir properties, or are we talking about the modeling properties? For example, what sort of relative permeabilities we are going to use? So, I mean, this question could be taken in different ways, but I'll answer in both ways. So for most of the rock properties and the rock fluid properties, we are going to take experimental results for the reservoir. And when it comes to this transfer functions, we are going to use the fine scale simulations as a proxy, where are we representing the same fluxes that happens through the fault. So that's going to be our basis for when it comes to representing the fine transfer functions. Yeah.
Okay, great.
I will have a question for you. I'm wondering, in your simulation case, you put the leakage area at some point in your domain. What happens if you don't have any priors on where the leakage will occur? So is your hybrid approach can be coupled with some adaptive meshes, or is it far away from what you're doing right now?
That's a great question, because that's the whole reason why we have built this model, because uncertainty is the big question here, because we really don't have any prior. So these are very ultra fast workflows where you can just enter, let's say you have a Monte Carlo distribution of you don't know. So you can do this, you can give an input, and the system will automatically grid where based on the realization, it will automatically grid. Let's say you can give a 2% fine grid, 1% fine grid around the fault, and it will, you can control the, so you have a lot of controls in this, and most of it is done automatically, so you don't have to worry about, am I doing the right, am I giving the right windows? Yeah.
Okay, so
Yeah.
it will be great to have this coupled with uncertainty quantification then.
Yeah, yeah, that's the next step of this work, where we are going to use this for uncertainty quantification, and that's the reason why we use a faster approach, because
Yes,
most of these models run really fast. Yeah.
Okay, perfect. Thank you very much.
Yeah.
Great. Do other people have any questions? Okay, so yeah, we go to the next speaker. We have Hannah Menke here from Heriot-Watt. Hannah is a research fellow at the Institute of GeoEnergy at Heriot-Watt University. Her research focuses on upscaling flow and transport in porous media using a combination of multi-scale imaging, numerical modeling, and machine learning. She is also a co-founder of the GeoChem Foam project, the world's most advanced open source power scale numerical solver. She did her undergrad in Earth and Environmental Engineering at Columbia University in New York, and a PhD and postdoc at Imperial College at London. Thank you, Hannah, for joining us. The floor is yours.
Thanks. Can you see my screen?
Yes, we can.
Awesome. Thank you for the invitation to speak today, and thank you all for coming. So I'm Hannah Menke, and today I'll be talking about some of the work we've been doing investigating the effect of structure on reactive dissolution, and a new type of dissolution regime that we found in our vision for upscaling these pore scale results to the Darcy scale. So when we examine rock dissolution, this dissolution has traditionally been divided into three regimes. So we've got this compact or phase dissolution at low flow rates, wormholing at intermediate flow rates and reaction rates, and uniform dissolution at high flow rates. However, when we look at more structurally complex carbonate rocks at the pore scale, and I've done quite a few experiments on these, we saw a new dissolution regime called channeling, where already existing flow pathways were widened by dissolution. However, it wasn't clear when we moved to the core scale where this new regime fit in the conceptual model of dissolution. So the question is channeling a type of wormholing? Is it a type of uniform, or something in between? And how does the porosity and permeability vary with this new type of dissolution? And this is a really important question when you want to upscale to the Darcy scale, if you want to have any hope of predicting dissolution at that scale. So we designed a study to find out. So we created two synthetic pore structures with varying levels of heterogeneity stochastically with Python. It's worth noting that these domains are far larger than any that had been attempted before with a pore scale reaction study, and had dozens of model runs. This was necessary to be able to do a representative elementary volume on the more heterogeneous model. And the distribution of pore throat sizes and velocity are shown on the right. So model A has a velocity and pore throat size distribution that are close to uniform, where model B shows a fat tail where the flow is focused in the preferential flow paths through the larger pore throats. So because we needed such a big model domain and we wanted to test many different flow and reactive conditions, our solver had to get better. So with the arbitrary Lagrangian Eulerian method, you track the interface. It's very accurate, but the problem is that as the mesh deforms, it becomes quite bad, and you need to remesh it. Otherwise, the simulation will crash. So we can do beautiful things like wormhole dissolution, but it takes quite a lot of time. However, when we use a steady state for both velocity and concentration, we are able to take a time step that's about 5,000 times larger and do a simulation of wormhole formation in about 46 hours, which is about 100 times faster than other methods. This method has been benchmarked and has been published in Frontiers in Earth Science. And actually, since doing this study, we've improved it further with the improved volume of solid method, which is 2.5 to 14 times faster again. And this code is available open source on GitHub. So we performed a series of numerical simulations on each of these models at different flow and reaction conditions using our open source solver. And here we ran simulations of dissolution in each domain with a spread of over 4 orders of magnitude in reaction rate and over 6 orders of magnitude in flow rate. And with both domains, we see channeling happening between the wormhole and uniform dissolution regimes. And those are the boxes outlined in red. And with these results, we can now confirm the existence of channeling and start to understand how pore structure impacts how channeling manifests. Furthermore, we can see that the porosity permeability trends, that the pore space heterogeneity, local flow, and reactive conditions change the porosity permeability relationship by orders of magnitude. And that furthermore, channeling, which is in red, has this inverse curvature that is distinct from either a wormhole or uniform dissolution, which will be important for upscaling. So let's zoom in a little bit and see what's actually happening. So here we have a rendering of the dissolution at various porosities through time, and the pore size distributions and how they change. So here's the compact case, which is relatively straightforward, with increasing complexity causing some minor instabilities, but not much. And then as we move to the wormhole case, they're also reasonably straightforward, with the increasing pore space heterogeneity causing instabilities earlier, resulting in earlier breakthrough in the wormhole case, or in the Model A case, and a higher porosity permeability relationship. And then in the third column, we see evidence of this channel formation right off the bat, both in this kind of fat tail in the throat size distributions, and then also you can see that there is initially some dissolution at the model outlet, even in the first time step. And you can also see that the higher heterogeneity model is more dramatic. And then in this last case, this is in the uniform regime, and we can see that their model is dissolved everywhere at once, except in Model B, there are some areas which have very, very low dissolution rates, where there's very low flow rates initially. And we think this is because the transverse dispersion is not high enough to transport reactive fluid throughout the whole rock. So now we can start to reconceptualize this conceptual model of dissolution with the addition of channeling. So channeling is a distinct regime. It's between wormhole and uniform, and it's not entirely clear exactly where this shift will happen with increasing structural heterogeneity. So that's a topic of future research. So qualitatively, we can tell apart wormhole and channeling from the shape of the porosity permeability curves, but we wanted to be able to quantify this. So we performed clustering on the results of all simulations to quantitatively identify dissolution regime. First, we extracted the 4 moments. That's the mean, standard deviation, skewness, and kurtosis of the distribution of concentration, velocity, and throat size at each time step. And on the right is an example of this pore throat extraction algorithm, where all the pore throats are identified at each time step. And then we used agglomerative hierarchical clustering for a range of numbers of clusters from 2 to 10, shown in figure B. And the numbers of clusters are ranked using the silhouette coefficient, which ranks the optimal number of clusters, where a higher coefficient indicates that the clusters are dense and well separated. And for our group of simulations, the highest silhouette coefficient was observed with 4 clusters. So this clustering identifies channeling as an independent regime. And then furthermore, the clustering dendrogram can show you how the clusters were split. And so you can see that uniform and channeling were split from compact and wormhole first, and then compact and wormhole splits, and then finally uniform and channeling. So this allows us to show the difference in dissolution behavior is greatest between channeling / uniform and wormhole and compact, and that in the smallest change in behavior between channeling and uniform. which strengthens our assertion that channeling is distinct from wormhole formation. Furthermore, it's interesting to note there are many simulations which exist on the boundary between regimes, beginning in one regime and ending in another, as dissolution changes the distribution of flow within the porous medium and flow becomes more or less stable in preferential flow pathways. So, okay, that's great, but some will say, well, that's only 2D. How does it compare to the 3D experimental results? So when we apply a power law fit to the porosity permeability relationship, we find the order of permeability increases very low, between 1.5 and 2 for compact dissolution. When we look at wormholes, it's somewhere between order 11 to 19. And for channeling, it's 6 to 12. And for uniform, it's 5 to 6. And when we compare this to experimental results in 3D, it's remarkably consistent. Previous experimental observations have seen uniform dissolution at order 5 and channeling at order 6 to 12. So while we can't say 100% for sure with these results, it looks like the additional complexity added in the 2D to 3D conversion is less important in terms of overall behavior with single phase systems than it would be with, for instance, multi-phase. So that's the end of this part of the presentation. And as a sneak peek for those of you who are attending InterPore, come see my presentation on Thursday to see how we have used this data set to train an upscaled machine learning model for dissolution that far outperforms traditional methods, and benchmark it against some enormous 4,000 squared pore scale models run on the Archer 2 supercomputer. So thank you all for listening, and I'd be happy to answer the questions either in the Q&A or by email.
Thank you very much, Hannah, for your nice presentation. And if there are any questions, please type on YouTube. And while we are waiting for some questions from the audience, I actually have one. To me, this transition to the different regime, including the channeling, uniform compact, reminds me a bit of the different phases in a totally another context, which is the one of the drainage events, in which we have a transition from uniform to fingering that can be either generated by viscous or capillary force. So can you maybe argument a bit about that? And in literature, these regimes
I mean,
are...
it is a balance of forces. I see what you're saying. Like in drainage and inhibition, it's viscous and capillary forces that cause these different patterns. Whereas here, I think it is kind of and we've been trying to prove this, but haven't gotten as far as we'd like. This dispersion transverse versus longitudinal, and how it propagates through this really complex porous media. So there is something there, but we haven't proved it yet.
No, sure. It was just a very naive, actually, observation. And maybe a suggestion, because I saw that this channel are pretty thick, but otherwise it would be nice to characterize maybe with fractal dimension to see also to characterize better the transition. Have you think about that? Is it, or if it is possible?
Yes, we're working on that, but we haven't.
Okay. Oh, yeah, that's fine. Okay. Thank you very much. We actually have a question from audience. So from Raid the Himalaya. Great talk, Hannah. I was wondering how having trapped phases, for example, CO2 ganglia, can impact these regimes.
So there are a couple of papers on this, but essentially what you get is that the CO2 ganglia, assuming that they're the non-wetting phase, block the biggest pores and pore throats. And so all of the dissolution, or the acid is directed around them. So you actually get what would, if you were in a single phase system, you'd be in maybe channeling or wormholing regime. But with two phases in the pore space, you'd end up with compact dissolution. Because all of this really highly reactive fluid, which would normally be drawn through the center of the pore throats, is pushed to the side. So it reacts the face of the rock really quickly. But I don't have any simulations to prove it.
Okay, very good.
I would also have a question, Hannah. Have you done any sensitivity studies about pores distribution on the tunneling behavior? Meaning, it depends on pore distribution and local heterogeneities also, and would it be interesting to have like benchmark on this?
So and this is sort of in the appendices of the paper on archive. So we designed the model B especially to be, it's generated randomly with Python, but with certain parameters. And so we actually generated many realizations of this model and made sure that the porosity and permeability and regime were the same.
For different,
yeah, so it's the same, stochastically the same, but different model pictures, if that makes sense. So that's the whole point of doing the bigger model, is that if you don't have a representative elementary volume, this would definitely affect your result.
Okay, great. Thank you for your answer.
Are there any other questions from the audience or from the participant here?
There is a comment again from Said, who was congratulating you. Well, so thank you again, Hannah. I think we can finish here. I would like to thank both of our speakers. It was a great session, and thank you again for being here and for representing Heriot-Watt University before InterPore. I would also like to advert for June Porous Media Tea Time Talk session. So we will have another special about Sirius Brazil new synchrotron facility. So we don't have the speakers yet, but stay tuned, and we will communicate about this in a few weeks. So meanwhile, this is our team. So it's increasing a bit. We have new members here. And if you like to be involved with the speakers, or to maybe subscribe only to our YouTube channel and newsletter, please feel free to contact us at porousmedia at gmail.com. And we will. It would be a pleasure for us to have you involved. So thank you again for the audience for being here, and don't forget to stay tuned. Bye.